Hey everyone, welcome back to another week of Physics 40B. Last week, you guys were introduced to oscillations and simple harmonic motion, which dealt with a lot of equations and trig functions. This week, we are talking about traveling waves, which is chapter 16 in your textbook. In this video, I will be focusing on discussing about what is a wave, some types and properties of waves, and going over snapshot and history graphs. All right, so let's begin. When we see the word wave, we typically think about the waves on the beach. Although that is a particular wave, in physics, it is defined as a disturbance in an environment that moves energy from one point to another. So, in a way, a wave at the beach also applies to this definition. If we consider one fluid particle in a wave, it requires some energy that pushes the fluid particle from the ocean to the sand. When we talk about waves, we also need to introduce other terminology. First, a medium is the fluid the disturbance travels through. Typically, the medium is water or air, but could be any other type of fluid. Another important term is propagation. This is just a fancy way of saying that something is moving or propagating because of the disturbance. When it comes to traveling waves, there are essentially two distinguishing types. The first is called a transverse wave. If I have a slinky, I first attach one end to the wall and hold the other end with my hand from a certain distance. If I move my hand up and down, I create a sine wave just like the one in the image. We see that the motion or displacement is in the vertical direction, but the wave is traveling in the horizontal direction. Therefore, the transverse wave is where the displacement is perpendicular to the direction the wave travels. Another way of looking at transverse waves also includes its characteristics. In this case, we can consider the top vertex of the transverse wave to be the crest and the bottom vertex to be defined as the trough. The second type of traveling wave is a longitudinal wave. If I have the same scenario as before, instead of moving my hand up and down, I am pushing and pulling the slinky in a horizontal direction. This shows that the longitudinal wave has the motion or displacement parallel to the direction the wave travels. The longitudinal wave also has its own characteristics. When we look at these waves, the sections where the slinky is the most compact is called compression, whereas the sections where it is farthest apart is called rarefaction. Because a traveling wave typically deals with a sinusoid, we can extract some properties from that wave. First is the amplitude, which is the maximum displacement or peak in the graph. Next is the wavelength, which is the displacement between two peaks that are next to each other. And finally, there is the frequency, which is the number of oscillations that occur within a second. These all should look really familiar because they are essentially from the oscillations and simple harmonic motion chapter. But we are also missing a few more properties specific only to traveling waves. The wave speed is basically how it sounds, the speed of the wave. It could be the speed of ripples moving across the water if a pebble is dropped into a lake, or the pulse that travels down a string. The governing equation of the wave speed of a string is the square root of t over mu. Here, t represents the tension of the string and mu represents the linear density, which is considered as the mass per unit length. When we want to visualize how waves travel, we can do so with two particular graphs. The snapshot graph looks at particular instances of time and show the displacement versus position. Think about the slinky example for transverse waves. If I take a picture at every half second of the wave, I basically have a collection of snapshot graphs. On the other hand, the history graph looks at particular positions and show the displacement versus time. If my eyes are fixated to one point of the slinky, it changes position or displacement over a period of time, which I can plot as the history graph. Let us now go over an example. If I drop a pebble into water and somehow capture the rippling effect, I get a sinusoidal graph. To simplify things, I can assume that the wave speed is 1 meter per second. Looking at the figure to the right, at t is equal to 0 seconds, I have a basic cosine graph. At t is equal to 1 second, the wave should move to the right by 1 meter because my wave speed is 1 meters per second. If I do this for 3 consecutive times with increments of 1 second, I can extract all the snapshot graphs for those instances in time. However, let's say we want to map or convert the snapshot graph into a history graph, specifically at position x is equal to 2 meters. How can we do that? Well, let's think about it. If I only want to analyze the position at x is equal to 2 meters, my eyes should be fixated to that particular point. I can draw a dotted red line at position x is equal to 2 meters and place markers of where each snapshot graph intersects the dotted red line. Remember, for a history graph, the x-axis is now time, so for each time from 0 to 3 seconds, we are putting the same displacements from the snapshot graph onto the history graph. And once that is done, we finally obtain the history graph by connecting the dots together. Okay, so we are finished with the first part of traveling waves. If you have any questions or concerns, please feel free to leave a comment down below or stop by our SI office hours, which are listed in the description link down below. Thank you for watching, and I'll see you guys in the next video.